Right. Oof. So we're equipped with the language of phase, coherence, and phase difference. And now we boldly go into a sort of zoomed in version of Young's double slits. We've got on the left, slit one, slit two. We pick a point in the middle of their slits. And the question I want to answer as a mathematician, as a physicist, is where are the maxima going to be in terms of angle? So what angle theta am I going to get before I reach my first maximum? There will be a maximum in the middle because these two light sources, they are coherent because they're sourced from the same ultimate light source. So they've got the same wavelengths, same. They don't have any phase difference. This point in the middle, the path difference between the light from the 2 points is going to be equal because they have to travel an equal distance. That's great. Therefore, they are going to constructively interfere. They've both had to travel the same pathway through our system, and they'll form a big central bright fringe. But as we saw on the previous slides, you get multiple fringes as well. So I want to know what angle is it where I'm going to get my next fringe. And we're considering down here, but there'll obviously be one up here as well. Okie dokie. Using a bit of algebra, we're going to say the distance between the slits and the screen is usually quite large, a matter of meters rather than micrometers or whatever. That's little d. The displacement vertically from the center of my screen is w, because it will be nice to know physically on my screen how far, are my fringes 30 centimeters apart? Are they 1 millimeter apart? Who knows? That would also be nice to discover. S is the separation of the slits. And X is a mathematically defined, is defined as the edge of this triangle. If I draw at right angles, this is not necessarily my finest drawing. If I draw the path from each slit to the point on the screen that I'm temporarily interested in, and I then draw a path parallel to that, X represents the path difference between them. Or rather, I'm going to draw this orange line, and X I'm going to define as the path difference. I'm then going to assert that more or less this is a right angle. The more astute among you might quibble that, but given how small this angle will end up being, the small angle approximation will sort out any pedantic quibbles we might otherwise have. I know that's a very physicist way of talking, but hey, we're doing physics, not maths, not pure maths. Lovely. Right, with that all in hand, then we've got our 4 defined lengths. We can say, look, there's similar triangles at play here because we've got our angle theta here. If I take, this is a right angle here, so this is 90 minus theta, that's going to be equal to this little, I've got 90 minus theta here, that's going to be equal to this tiny little angle in here, and therefore this angle is also going to be equal to theta. Oh, sorry. Don't worry too much about the equivalence between those two thetas, but I can assure you they are the same. Therefore, given they're both right angled triangles, it means all the angles are the same. Therefore, angle, 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 they are similar triangles. Great. That means x as the opposite side of this triangle, the ratio between x and s, the opposite and the hypotenuse, is going to be the same as the ratio between w and d. Now you might again say, hang on, Mr. Bruce, this is crazy. D isn't the hypotenuse of my big triangle. And I will say, yes, you're right. But again, and this is another dirty trick, again, we are making the assumption that theta is small. Yeah, it's way, way, way less than 90 or whatever. And therefore, the small angle approximation says that sine theta is roughly equal to tan theta. In other words, the ratio between the opposite side and the hypotenuse is roughly equal to the ratio between the opposite side and the adjacent. And that's roughly equal to theta itself anyway. Okay, so once again, slightly hand wavily, we're going to say, look, you know, similar triangles, the ratios are pretty much the same. Okay, here's where the physics comes in. If we are going to form a maxima, the path difference between these two needs to be a whole number of wavelengths. X has to be a whole number of wavelengths. It could be 0, but that represents the situation where it's in the middle. The next order of maxima will be when n equals 1, and then n equals 2, n equals 3, so on and so forth. So we're interested in deviations away from the middle where the path difference is a whole wavelength, because then the two waves coming from these two sources, two slits, will be back in phase, which is lovely. Okay, so set x equal to n lambda, and w is going to be a standard spacing between slits, so set that equal to n w. At any rate, let's set them both equal to 1 because we're interested in the first order slits. Rearrange and you will find, look, here's an expression for how far apart these maxima are. Great, so that's the spacing of the fringes on my screen. Oh, sorry, there's a bit of a lag there. Whew. That's a little bit mathematically intense. I don't think I've ever seen an exam question where you're asked to do that. But I've presented it there for you just so you vaguely know what's going on. You might be asked similar question perhaps with a reference to diffraction gratings, but the maths is more straightforward and there's not so much underhandedness with small angle approximations and such. Okay, interference patterns. Diffraction and interference through a grating formed of many slits. Sorry, I'm just checking the time that we're supposed to finish this. Okay, we've got 25 minutes. We should be fine. If anything, we can actually afford perhaps to slow down a bit. Maybe. Let's see how we go. Diffraction and interference through a grating formed of many slits. A diffraction grating produces a similar diffraction pattern to the double slits. You end up with, you know, this big bright central fringe, and then you've got standard spacing between them, but they die off exponentially. For a diffraction grating, we won't go through we probably don't have time to go through the diagram in detail here. The equation's a little bit simpler. D is the spacing. N is the order of the fringe. So you can set it equal to 1 and you'll calculate fringe, the first fringe, except the central one. Lambda is wavelength. And then theta is the angle at which you will find. So it's this angle here, the angle at which you'll find that maxima or maximum. So this is the spacing in terms of meters. Wavelengths in meters or nanometers, whatever. So that is the space between each of our slits on our grating. Plotting intensity of the waves against angle gives the graph below. Okay. So you still have destructive interference. And you still get peaks. But the peak intensity does reduce. You get this sort of envelope of peak intensity dying off. Okay. With a diffraction grating, what perhaps looks most different, however, is that the peaks are pretty sharp. You can see on this diagram and this drawing in the top right that it's like only certain set angles, you know, like a laser beam. Yeah, that is more indicative of a diffraction grating than the double slit. The double slit is quite gentle, the spacing between the gratings. Okay, let's have a go at this exam question then. Two loudspeakers produce coherent sound waves. I'm glad they're coherent. Frequency 110 Hertz. They've got the same frequency, therefore, and the same phase difference. Or, you know, they're in phase. They're positioned at A and B, as shown in the following diagram. The speed of sound in air they give us is 330 meters per second. An observer begins at C, which is 30 meters from both A and B. State and explain what an observer moving from point C to D would hear. 5 marks, quite a lot. Okie dokie, so we're given this diagram. Not the world's most friendly diagram, it's got to be said. And we want to, an observer moving from point C to D would hear. So point C is 30 meters from both A and B, i.e. equidistant. Nice. Okay. Although we are used to the double slits in terms of the double slits in terms of light, you know, lasers passing through both perhaps, or, you know, even a light bulb. Here we don't have slits, but we do have two sources. It is analogous. We've got waves. There's no reason we can't apply the same maths. Okie dokie. So we're given the speed of sound, so we might as well use it. We've got a wave equation. We are not, what are we told? We're told the frequency, but we don't know the wavelength. So it'd be nice to work out the wavelength. 330 divided by 110. It's nice how those numbers work out. 3 meters is our wavelength. The constructive interference occurs when the path difference is some multiple of 3 meters. Destructive interference occurs when it's, you know, or maximum destructive interference, I guess, occurs when it's a half number of those wavelengths. So 1.5 meters or 4.5 meters, and so on and so forth. At point C, the path difference. When I first read this question, I was a little scared that they were gonna, oh, you know, we're gonna have to do some trigonometry. But actually, the fact that they give us these two is of great comfort. We don't need to bother with, you know, drawing this and working out what the path differences and so on and so forth. None of that is necessary. Surplus to requirements. Instead, we can just say, well, the path diff is 32 minus 27.5. So that's 4.5, which is 1.5 times our wavelength. That's no good, or well, it's not no good, but it means when you're at point C, you're at a point where there's destructive interference. Am I getting that way around? No, and when you're at B, you're at a point of destructive interference. C, constructive interference. Great stuff. Okay. The question is to state and explain what an observer would hear. So if you're starting, it says after moving from point C to point D, C, I'm already getting confused again. C, we said, is constructive interference. So you'd hear the music or whatever they're blasting, a podcast, the rest is history, or whatever you're into. They're blasting it out of their speakers. You'll hear it perfectly clearly. In fact, you'll hear it louder than you would from either one individually. As you move to D, you suddenly won't hear anything. Or, the world's not necessarily as perfect as our lab set up. The sound is loudest at C and quietest at D. The reason I sort of hedge my bets a little bit is because, it's a sound wave. It's probably bouncing off of things in the locality and bouncing off the floor, etc., which slightly spoils our laboratory assumptions. Between C and D, there's an additional maximum corresponding to a path difference of C. This is a very good point, easy to miss. If we are going from a path difference of 0 to a path difference of 4.5, we would have had to have passed through 1.5, where there's a minimum. We'll also have to pass through 3, where there's a maximum. So I guess what you will hear is it's on, it's at a minimum, it's at a maximum, it's at a minimum, and that's the story so far. Therefore, sound starts loud at C, gets quieter, gets louder again, then gets quiet again.